ఇంకా ఓపెన్. My name is A. Ramu. I am from ECC section. Subject is ptsp. The topic is general learning modeling for AUV position tracking. Here the slide is for any process and model for filter based SLAM algorithms such as EKF SLAM, fast SLAM and UKF SLAM. The current pose is only derived from the last movement pose according to their iterative nature compared with air ornament. The water directly interacts with AUV, which has a greater impact on the motion state of the AUV. The existence of the ocean current, turbulence, and eddy current, etc., set obstacles to the establishment of the process model by bringing various process noises. For the unnamed vehicles UVS and unmanned aerial vehicles, the camera is used to detect external environment features. Due to high pixel of the camera, the same feature are easily identified and associated. Thus the correct data association can achieve the correction of cumulative error for filter based algorithms such as EKF SLAM and fast SLAM and UKF SLAM. Unfortunately, the uses of the camera is greatly limited underwater. The next slide is about it is because there is a lack of deep sea and the presence of impurities also causes the water to be turbid. It is difficult to obtain environment information in water by using optical imaging. Thus the sonar which use the principle of imaging is implied to get underwater environmental information. Taking into account the fluctuations of AUV is the water as well as the effects of the marine life, the water quality, etc. The correct data association of sonar imaging is much less than that of optical images. Therefore, the performance of EKF SLAM, fast SLAM, greatly reduced. Here the picture about that. Since the measurement model and process model are complementary, if even if we get a previous process model, we can still cannot get a accurate positioning while using a rough measurement model. Furthermore, once the measurement is inaccurate, the correct data association is impossible and extra effort should be required to correct all the sensor errors from installation, which is also an important source of measurement error. Therefore, it is a key to reduce the cumulative error by establishing an accurate measurement model, especially for underwater robots. The modeling of process measurement is considerably vital for AUVs that are required for high precision navigation and positioning. Conventional analytical modeling approaches are fairly cumbersome and complex, which requires repetitive work and fine tuning for different platforms and sensor configurations. Therefore, how to design a general model that enables quick and efficient implementation of essential problem in AV position tracking. Here the picture of GPS and UKF SLAM and improved UKF SLAM. They giving the graph taking 0 to the y-axis is taken to 0 to 400, means the unit 1 unit is equal to 100 meters, and the y-axis taken 50 50 comparing both. The Gaussian process recognition GPR is attractive because of its flexible non-parametric nature and Computational simplicity. In recent years, GPR has been used in many fields, including image processing, medicine, and also for robots. However, it suffers from high computational cost, which is not suitable for online learning. Process models also integrated into different variations of voice voice filters. Unfortunately, enhanced accuracy of GP voice filters comes at the cost of increased computational complexity and the need for training. All data covers the the complete operational space of the dynamical system. Therefore, GPR is not suitable for AUV to perform tasks in large scale environment. The main limitation of GPR is that the computational complexity is proportional to training examples. To solve the problem of high cost, several lo- local gaussian process LGB regression was proposed by without sacrificing much accuracy than GPR. LBG regression can achieve online learning using nearby local models. In 2010, a new GPR model which clusters the input space into smaller subsets was proposed, which is worked similar to 16. The cost is significantly reduced by the user of smaller local models. Performance by establishing more accurate process and measurement models of AUV in order to obtain better position accuracy under the rough model provided by different algorithms. The general learning model is proposed. This general learning model consists of measurement learning model and process learning model compared with the measurement learning model, which is more dependent on sensor accuracy and need not to be carried out online. The process learning model is to the external environment, especially in complex underwater environments. Therefore, it's more demanding for the process learning model to achieve real-time online processing. However, end-to-end real-time on learning would be infeasible due to time and memory complexity. Therefore, the process learning model defined by global process learning offline and local processing online. Also, LPG does not take on this paper contains the following contributions. A general learning model has been proposed which take advantages of both LGB and hidden layer neutral networks to provide more accurate process and measurement model for AUV. The proposed learning model has been incorporated and tested on EKF SLAM and FAST SLAM and UKF SLAM such that general state tracking frameworks are proposed. The proposed framework has been demonstrated effectively in improving position tracking performance without a landmark in harsh underwater environments. Here the figure is given that here figure is given about that and the non-linear measurement model and process model of AVs are follows. ZK is equal to H of HK into SK plus pi K ZK minus 1 UK minus 1 XI is equal to Fi of XI minus 1, where HK of SK represents the rough measurement model which does not need to be accurate enough, and pi of K ZK minus 1 UK minus 1 is the learning model denoting the error between the rough model and actual measurement. The robot state that the KTH time step is denoted by XK. Fi into Xi minus 1, UI represent the rough process model under control input. Learning model indicating the error between rough model and actual robot states. A measurement learning mode. Here the picture of model predictive controller. Cost function is constant. Optimization is by system model. Optimization is give cost tracking model of AVS by IGAIN observer. Conclusion, we propose a non-linear model based on the hidden layer, neural networks, and local Gaussian process regression. The hidden layer neural networks have short training time, whereas the local Gaussian process regression is time, whereas the local, according to the above mentioned advantages of hidden layer neural network and local Gaussian process recursion, we get the measurement learning model and global process learning model offline and local process learning model in online. Then the proposed learning based models have been applied to the extended Kalman filter simultaneously uh, localization and mapping EKF slam row blacklisted and in mapping faster slam and unscented Kalman filter localization and mapping UKF slam for autonomous underwater vehicles position tracking with the field experiments. Thank you for giving wonderful opportunity.